Welcome to Math Primer for College Physics. So this is a review of basic mathematical skills that you will need to succeed in College Physics 1 as well as in College Physics 2. Please go ahead and look at the description because there I have listed all these sections that I'm discussing along with their timestamps. So you may already know one section, and if you want to jump to a different section, look at those timestamps, and then you can go back and forth within the video. I'm going to first talk about exponential rules and then give you some examples on it. When it comes to a number like this, 10 to the power 5, this 5 is what we call an exponent. This number 10 over here is usually called the base. So this is 10 raised to the power 5. Now these are the rules that you will need to simplify certain expressions, especially scientific notations. You will come across those scientific notations frequently in physics, and this is a very, these rules are very important when you try to simplify those. So let's look at the first rule. So you can see ax times ay, so that means a is the base and the two numbers have the same base. And in that case, the exponents simply add up. For example, I'll use base 10 like 5, 10 to the power 5 times 10 to the power 2. I can write this as 10 to the power 7, where I add the two exponents. The second one is a division between two numbers. Again, the bases are the same. So as an example, I'll write 10 to the power 6 divide by 10 to the power, let's say 3. So I can rewrite this in this way, over 10 to the power 3. And then as given in this rule, you simply subtract the exponents. And then your answer would be 10 to the power 3. The third one, again, you have a to the power x, and you take the power of that entire expression. So then the exponent simply multiply. You need to multiply the exponent. So let's say 2 raised to the power 3, and then the entire thing, we take the cube of the entire thing. And in this case, the answer would be 3 times 3 is 9. 2 raised to the power 9, like that. So this one is for this. That's the example, and this is this example, and then this covers this example. So the next one, let's look at this one. So you have a over b raised to the power x, and the exponent simply is distributed for the numerator as well as for the denominator. Now you can see the bases are different in this case. So let's take an example like this. 3, and then you are distributing the exponent in the numerator as well as the denominator. So you have 5 raised to the power 3 divided by 7 raised to the power 3. And sometimes, you may be able to simplify this further, provided that this is one number, one expression in a larger expression, or at this point, if it's not the case at this point, you can simply use a calculator to find the numerical answer. The other rule is the negative exponent. So that means, let's say you have this number 5 raised to the power negative 3. You can simply take the reciprocal of this. 1 over, if you take the reciprocal 1 over number, then the sign of the exponent changes. So if it's negative 3, then it becomes positive 3. Similarly, if you have this 2 raised to the power 3, then its negative exponent is given like this. 1 over, if you go 1 over, then the exponent changes, the sign of the exponent changes. The next one, fractional exponent. So For example, you have something like this, 10 raised to the power 6, the square root of that. So the square root means simply take the exponent 1/2. So 10 raised to the power 6 multiplied by 1/2, right? So then 6 and 2 cancels out, so you get 10 to the power 3. Or we can think about like a cubic root, 10 to the power 6. So in this case, again, we can simplify this, 10 raised to the power 6, and the exponent is multiplied by 1/3. And then you can see the answer would be 10 raised to the power 2 or 100. And the final rule, it's a very simple one. Irrespective of the base, you can have any number for the base, but if the exponent is 0, that's equal to 1. Okay, so it could be like 10,000, but still it's raised to the power 0. Exponent is 0, so then the answer is unity. It's just 1. 525 raised to the power 0, still it's going to be 1. So these are some of the most important exponent rules that you should know, that will definitely help you when it comes to simplifying mathematical expressions. Now let's do some examples. So I have two examples. As mentioned here, exponent rules are important when simplifying numbers involving scientific notations. So let's try to do the first example over here. You can see if you look at the numerator, the bases are the same. Again, the denominator, the bases are the same. So I'll basically add up all the exponents in the numerator. So I'll get 10 raised to the power minus 15 plus 4 minus 3, and then divide the entire thing by 10 raised to the power minus 5 plus 13, and then the numerator simplifies into, so minus 15 plus 4 minus 3, so that's minus 14, and in the denominator 10 raised to the power positive 8. Now further simplification means I can take this denominator with the exponent to the numerator, and the sign of the exponent will change. So I'll have 10 raised to the power 14 minus 8, giving me the final answer 10 raised to the power minus 22. So that's the simplified answer for example 1. So example 2, again we can see the first term, the base is 3 raised to the power 2. So keeping that base, I'm going to simplify that part. So 3 raised to the power 2, and that again has an exponent 6, and then we have 3 raised to the power 2. Again, the exponent of that entire thing is 2. Then division, 3 cubed raised to the power 2. So the first part I can write it in this way because we have the same base. I can write it as 6 minus 2. The division, I can do this. I can multiply and then take the reciprocal of this, like this. Okay, and then here 6 minus 2 is 4. So I have 3 raised to the power 2 multiplied by 4. And here in the denominator, multiplied by 1 over this number means basically this, 3 cubed raised to the power 2. So then I can multiply the exponents. I'll have 3 raised to the power 8 divided by 3 raised to the power 6. You can see again the same base. So finally I can write this as 8 minus 6, giving me 3 squared or 9. So that is the answer for this example. So this basically gives you some idea about exponent rules and how to apply them to simplify expressions, which is very important, as I told you, in physics. Another section that is important is solving simultaneous equations. So I'll explain this using these two examples. So the first example gives you two equations, 2x plus y equals 9, 3x minus y equals 1. So we have to solve them and find x and y. So I see a plus y and a minus y. So what I'll do is that I simply add these two equations together, and then I'll be eliminating the y variable. So I have 2x plus y equals 9, and then I have 3x minus y equals 1. I'm going to add the two equations, and then you'll see the plus y and the minus y will cancel out. On the left hand side I'll have 5x, on the right hand side I'll have 10. So I'll divide everything by 5, and then I'll have x equals 2. Now in order to find y, I will substitute this x value in one of these equations. So I'll use the second equation. So that means 3x minus y equals 1. So I'll substitute for x the 2 minus y equals 1. I'll have 6 minus y equals 1. So I'm going to move the y to the other side, plus y. So I'll add a plus y here. So then you can see these two cancels out. 6 equals 1 plus y. And then I'll remove the plus 1 to the other side by adding a minus y to both sides. And then these two will cancel out. So you can see then I get y equals 5. So those are the two solutions for this set of equations. You can always substitute these solutions back into the original equation, that is x equals 2 and y equals 5, and see if these are satisfied. So that's how you check whether your solutions are correct or incorrect. Let's go to the second examples. This is a little bit difficult than the first example. We can see there's a minus 2y and a plus 3y, but if you simply add the two equations, you are going to still see a y variable. So as a result, I'm going to do a different technique, but let me first number these two equations as equation 1 and 2. I'm going to multiply equation number 1 by 3. So multiply by 3 equation number 1, and then I'll get 12x minus 6y equals 12. And then I'll multiply equation number 2 by 2. So 2 multiplied by equation number 2, which will give me 10x plus 6y equals 32. Now I have these two equations, and now I'll see that there's a minus 6y and a plus 6y. So I'm going to use the method of elimination to simply get rid of the y variable here. So I'll add these two equations together, and then I'll have 22x. These two will cancel out, and then I'll have 44 over here, and then I'll divide the entire expression by 22, and then I'll get x equals 2 as one of the solutions. And then again I'm going to substitute x back in one of these equations. I'll use equation number 1 for example. So I have 4x minus 2y equals 4. Substituting 2 for x, I have minus 2y equals 4. Then 8 minus 2y equals 4. I'll add a plus y, 2y over here, and then I need to do the same thing on this side to get rid of the negative 2y. I have 8 equals 2y plus 4, and then I'll subtract 4 from this side, so I have to do it on the other side as well. So then these two will cancel out. So then further simplifying the equation as 2y equals 4, divide everything by 2, and I get y equals 2. Okay, so you get x equals 2 and y equals 2. I showed you step-by-step methods of simplifying these expressions, but you should practice these things, and you should actually try to do these things very quickly. Even skipping one or two of these steps would be fine, but in order to explain what actually happens, that's why I wanted to show these all these steps. So again, you get x equals 2 and y equals 2. Substitute these solutions to the original equations and see if they satisfy the equations. If that's the case, then your solutions are correct. Solving quadratic equations is again something important, and I want to review that in this video. So if you are given a quadratic equation like this, ax squared plus bx plus c equals 0, the solutions, or sometimes we call them the roots of the quadratic equation, are given by this expression. We call this the quadratic formula. Inside the square root, you can see b squared minus 4ac. So this b, a, c, those are the coefficients of these terms in the quadratic equation. So this term b squared minus 4ac is called the discriminant. So this has a special name. It's called the discriminant. And depending on the positiveness, negativeness of the discriminant, your solutions will differ. For example, let me denote this by uppercase D. And if D is greater than 0, that is D is a positive value, then you are going to get two solutions, two real distinct solutions. If D is equal to 0, then you get two solutions, but they are equal to one another. So two real solutions, but equal. Okay. And then the next case is when D is less than 0, that is D has a negative value, then your solutions are imaginary, or we call the roots are imaginary. So this is something that you need to know when you're solving a quadratic equation, especially using the quadratic formula. So let's look at these examples. So here you have to identify what are the coefficients. So directly I can see the coefficient A equals just 1, coefficient B is equal to plus 5, and coefficient C is equal to minus 14. So then I'm going to make a substitution in this equation, in this formula, quadratic formula. I'll have minus 5 plus or minus square root of 5 squared, which is 25, minus 4 times 1 minus 14. And then the entire thing has to be divided by 2 times the coefficient of coefficient of the first term, which is A equals 1. And then when I simplify this, I'm going to get, let's see, minus 5, and then over here I have 25, and minus 4 multiplied by minus 14, I'm going to get 4 times 4, then it will be a plus value, 16, and I get 56, and then divide this entire thing by 2. So it's a matter of simplifying this expression, plus or minus square root. Here I'll get 1, and I'll get 81 here, and then divide by 2. So you should know the square root of 81, which is just 9. So I get x equals minus 5 plus 9 divided by 2, and x equals minus 5 minus 9 divided by 2. And you'll see the solutions for this quadratic equation is x equals x equals it's going to be, x equals 2 and x equals, that's going to be minus 14 divided by 2, minus 7. Okay, so those are the solutions for this quadratic equation in example number 1. Let's look at example number 2. So again, I'll identify the coefficients. Here in example number 2, a would be 2, then b is going to be minus 14. So remember to put the sign if there's a sign. And then c is again a negative number, minus 13. So I'm going to substitute these coefficients in the quadratic formula, and then I'll get x equals, there's a minus sign, minus 14, plus or minus, then inside the square root I'll have minus 14 squared, and minus 4 times a is 2, and then c is minus 13. And in the denominator, I have 2 times a, which is 2 times 2. So it's a matter of simplifying this. So if you simplify, you'll get plus 14, and inside the square root, you can do the calculation and you'll see this, you are going to get like 300, which is a positive number, and then divide the entire thing by 4. Again, you can simplify this. You can take out, you can simplify the square root of 300, and then divide everything by 2. You get 7 plus or minus 5 square root of 3 divided by 2. So your answers would be x is 7 plus 5 square root of 3 over 2, and x is equal to 7 minus 5 square root of 3 over 2. So both these numbers are real, distinct numbers. So the solutions are real. There are 2 solutions. They are real and they are distinct, just like example number 1. So this should give you an idea about how to solve quadratic functions using the quadratic formula, which is shown here. Let's look at some geometric shapes that will be important for this course. So a circle, you need to identify what is the radius. It's the distance from the center of the circle to the edge, and the diameter is twice the radius. So diameter is usually denoted by d. So d is equal to twice the radius, where radius is represented by the lowercase r. Circumference is the length of the perimeter, what we call the perimeter, and that's given as 2 pi r. And also you can express this same thing in terms of diameter instead of using the radius, and then it will be pi times d. Area of a circle is pi r squared, where r stands for the radius. Again, you can represent this in terms of the diameter, then it would be pi d squared over 4. So these are important things that you have to remember, especially in this course. Now let's talk about the surface area of a sphere. Again, the radius of the sphere is given as r. In that case, it would be 4 pi r squared. Okay, again, try to write this in terms of the diameter. Sometimes instead of giving the radius, one could give the diameter. So you should be able to write all these quantities in terms of radius and in terms of the diameter. The volume of a sphere is given as 4 over 3 pi r cubed. Always remember, when it comes to the volume, the radius varies as r cubed. If it's a surface area, the radius varies as r squared because surface area is two-dimensional. So that means it's proportional to radius squared. However, volume, it's three-dimensional. You have a length, a width, and a height, three dimensions. As a result, radius to the power 3 or cubic. So that's an easy way to kind of distinguish areas versus volume. Now let's talk about a cylinder. The area of a cylinder can be broken down into this curved surface and these top and bottom caps. So the total area would be the area of the two caps, which is 2. The cap is basically a circle, so I have 2 times pi r squared. R is the radius, you can see h is the height of the cylinder, plus now the area of this curved surface. So that is written as 2 pi r times h. Okay, so that gives you the surface area of a cylinder. Now the volume of a cylinder is simply the area of the circle multiplied by the height. So that is pi r squared times h. This gives you the volume of the cylinder. So these are some of the important geometric shapes that you need to know, especially how to find the area, how to find the volume of these geometric objects. And that's, again, as I told you, will be important in this course. Okay, we will continue geometric shapes. There are 5 types of angles that you need to know. They are right angles, straight angles, acute angles, obtuse angles, and reflex angles. So a right angle, obviously, something like this. There's a 90-degree angle, and that's what we call a right angle. A straight angle is like a straight line. Let's say that there's point O, and then you measure the angle like that, and that will give you 180 degree of an angle, and that's a straight angle. An acute angle is an angle that is less than 90 degrees. So something like this. So let's say this angle, like it could be like 30 degrees. So it's less than 90 degrees. Usually we denote the angle by the Greek letter theta. So in this case, generally I can represent it as theta less than 90 degrees. And that's called an acute angle. And then the fourth one is called the obtuse angle, that is larger than 90 degrees. So something like this. This is O, and this angle over here. Let me again denote that by the Greek letter theta, and whenever theta is larger than 90 degrees, we call that an obtuse angle. And the fifth angle that you need to know is called the reflex angle. So again, something like this. But now instead of looking at this angle, we look at this angle. That's our theta. So here, theta is larger than or greater than 180 degrees. Okay, so that's when we call that's an angle we call a reflex angle. So these are the 5 types of angles that you need to know. Now let's look at a triangle. Especially finding the the perimeter of a triangle should be straightforward, but sometimes people have difficulty in finding the area of triangle. So here I have a right angle triangle. Let's say that this is obviously a right angle. You can see that. So the general formula for finding the area of a triangle is 1/2 multiplied by the base of the triangle multiplied by the perpendicular height drawn to the base from a vertex. A vertex is one of these points. Like any of these points, we can call them vertices, or like singular form is vertex. So that's a vertex. Okay, so perpendicular height, or simply 1/2 base multiplied by height. So if we use that for this 90-degree angle, the right angle triangle, we get 1/2 base is given as b, and the vertical height is this one, h. Again, if you have a triangle like this, identify the base, that is this one, and the vertical height is this height. Okay, so again for this, this is for this triangle, and the expression here, it would be the same, 1/2 b times h. If you have a triangle like this, you can still identify the base. So you have 1/2 b, and the height, vertical height, how do you find the perpendicular height? Extend this line from the base and then draw a perpendicular from the vertex to the line that intersects the perpendicular line, and you'll see that height is the same height, h. So basically this is the equation that you need to understand when finding the area of a triangle, any type of triangle, 1/2 base times the perpendicular height. In this section, we are going to talk about proportionalities and ratios. Proportionalities are important when we talk about relations. So there are 3 relations given here. Each one of these will have something called an independent variable and a dependent variable. So the first 2 relations are direct proportionalities. So that means when one variable is increasing, the other variable is also increasing. When one variable is decreasing, the other variable is decreasing. This symbol over here, it looks like alpha. So that's what we call the proportionality symbol. So the first relation and the second relation are direct proportionalities between the 2 variables, but the third one is an inverse proportionality between the 2 variables. So that means when one variable is increasing, the other variable is decreasing, and vice versa. So these are the 2 types of proportionalities that we'll see: direct proportionalities and inverse proportionalities. So we can combine these 3 relations and write this expression. Now, if we want to convert this to an equation, what we need to do is that we need to multiply the relation by something called a proportionality constant. Here it's represented by k. Now, when we multiply that, we get equation number 1. Now, suppose x3 variable is doubled. So that means in the denominator, you can see a 2 here. And as a result, we end up with a new equation. And that's why I call it equation number 2. Now we can use equation 1 and equation 2 to find the ratio between y and y prime, because this is something that we usually find in physics, finding the ratios, finding the proportionalities, things like that. So the ratio can be written like this: y, this colon-like symbol, y prime, or we can write it like y to y prime, or even like a fraction, y over y prime. So these are 3 ways of representing a ratio between 2 variables. So in this case, let's look at this example. equation number 1 and equation number 2, if we want to find the ratio between y and y prime, I'm going to write it like this. So from equation number 1, y is k x1 x2 over x3, and y prime is k x1 x2 over 2 times x3. So you can see the common terms. If I simplify it further, removing the common terms, I will have 1 1/2 like that. So that means y over y prime can be written as 1 over 1/2. So in other words, it's like 2. So finally, I can write y with the ratio between y and y prime as 2 to 1. Okay, so this simplification, this identifying the proportionality, writing the ratios, simplifying the ratios is very important in this course. So that's why I want to review it like this. Okay, let's try to do these two examples that are related to proportionalities and ratios. So in the first example, you are supposed to find the ratio of P1 to P2 to P3, provided you are given P1 equals I squared R1, P2 equals I squared R2, and P3 equals I squared R3. You can see that I squared is common in all these three equations. So P1 to P2 to P3 can be written in this way: P1 to P2 to P3, and then that's equal to I squared R1 to I squared R2 to I squared R3. So I squared is common, so then what I can do is that I can remove that I squared from the entire expression, and then I'll have R1 to R2 to R3. So that's one way of writing it. Another way to express the same relationship is use like fractions. So I can write the same thing as P1 over P2 is equal to R1 over R2. And also I can write P2 to P3 is equal to R2 to R3. And if I want to, I can write the other one as well. P3 over P1 is equal to R3 over R1. So it's the same way. So this representation over here is identical to this representation. It gives you the same mathematical idea. Okay. The second example, find the ratio between the original volume to new volume if the radius of a sphere is tripled. So you should know the general formula for the volume of a sphere where the radius is r. So that's given as 4 over 3 pi r cubed. So let me call this the original volume. So the new volume, according to the data given, is equal to when you triple the radius of the original sphere. So that means 4 over 3 pi. Instead of r, now I need to put 3 times r and cube the entire thing. And as a result, you can see there's a factor of 3 to the power 3, which is 27, coming from this expression. So I have 27 times 4 over 3 pi r cubed. So in terms of the ratio, I can write this as V original to V new as 4 over 3 pi r cubed to 27 4 over 3 pi r cubed. Now 4 over 3 pi r cubed is common, so we can remove that, and we can simplify the ratio as 1 to 27. Okay, so this is one way of writing this. The other way is as a ratio, just like in the example 1, V original over V new. I can write this thing 4 over 3 pi r cubed divided by 27 4 over 3 pi r cubed, and then you can see these two terms cancels out, so I have this 1 over 27 ratio. So it's mathematically this way of getting the relationship. The final outcome is identical to this way of representing it. So these are two examples to give you an idea about how to deal with proportionalities and ratios. In this part, we are going to look at logarithmic rules and logarithmic functions. So there are two forms of logarithmic functions, the base 10 logarithms and base e logarithms. Sometimes base e logarithms are called natural logarithms, where e stands for e has a numerical value of 2.718. So these are some important rules that you need to identify. So if there's a product and you take the logarithm of that product, that's equal to the sum of the logarithms. So for example, if you have something like this, ln 25 times 3, we can break it into ln 25 plus ln 3. Okay, this symbol, you can see these two parallel lines, that gives you the modulus. It basically tells you just take the magnitude of that number. So for example, if you take the modulus of, let's say, minus 9, negative 9, that's equal to 9. Okay, like that. So in this rule is the ratio. If you take the logarithm of a ratio, that's equals to the different of the separate logarithm. So again, 25 over 3, if you see something like this, you can represent it as ln 25 minus ln 3. Now this one, the power rule, a very important one. So let's say you have 10 raised to the power 3, then this can be represented as, simply expressed as 3 times ln 10. Another one, important one, is, let's say you have ln 1 over 4. So you can rewrite this 1 over 4. You can move the 4 to the numerator, and then its exponent becomes a negative value, like that. And then you can apply the power rule, minus 1 ln 4, like that. So these are some rules that you should familiarize in order to do problems related to exponents and exponential functions or logarithmic functions. So let's try to solve this problem. So we need to solve for t. So what I can see that there's an exponential function here. I'm going to in order to remove the exponential function, I need to take the logarithms. This is a base e function, an exponent, so I'll take the natural logarithms on both sides. So ln 1 over 4 is equal to ln e to the power minus 5t. So then I can simplify this as minus 1 ln 4, as I showed here, equals, when so ln is the anti-operation of exponent, so then this becomes minus 5t. So you can see the minus sign simply falls off from the equation, and then I can solve for t, which is ln 4 divided by 5. So that's how you simplify this particular equation to solve for the variable t. Okay, in this section we are going to briefly talk about the number line and the xy coordinate plane. So the number line is a one-dimensional system to measure position relative to a reference point. So the reference point here is 0, as you can see. Anything to the right of the 0, that's considered positive numbers, and to the left they are considered negative numbers. So if you move to a position like this relative to the origin, then we call it like, +3 or 3 units to the right. And if you move to a position like this, that is -2, we can say 2 units to the left. So that's how we use a number line. It's one dimension. One side, usually the right hand side, is considered positive. Left hand side is considered negative. When you put two number lines perpendicular to one another and construct a two-dimensional grid, that's when we call an xy coordinate plane. So remember, simply a number line is one-dimensional. In the case of the xy coordinate plane, that is two-dimensional. So that means you need two coordinates to specify a position. We can define, when we have the xy coordinate plane, we can define 4 quadrants. So this is the first quadrant, this is the second quadrant, third quadrant, and the fourth quadrant. And in each of these quadrants, relative to the origin, we can represent a particular position. So for example, over here, how do we define that position relative to the origin? First we write its x coordinate, which is 4, and its y coordinate is also 4. If we think about a point in the second quadrant, the x coordinate is -6, whereas the y coordinate is 1. A point like this in the third quadrant, x coordinate is -3 and the y coordinate is -2. And in the fourth quadrant, if we consider a point like this, its x coordinate is 2 and its y coordinate is -4. So that's how we represent positions in the xy plane relative to the origin. Since it's two-dimensional, you need 2 points to define, 2 coordinates to define a position, but on just a one-dimensional number line, you just need 1 coordinate to specify the position. In this section, we are going to talk about a very important theorem in math that is extensively used in physics. That's called the Pythagorean Theorem. So we need a right angle triangle to discuss the Pythagorean Theorem. And just for simplicity, I'm going to use a right angle triangle in the first quadrant. So I'm going to select the triangle. So this is one side, you need 4 units. The other side is 3 units, and then I have the third side like that. And then the Pythagorean theorem talks about the areas that are made by these sides. So here I have this side, you can see it's 3 units. The area of squares, so if I construct a square over here, so this area, so let me call this side A, and let me call this side B, and this side C. So the area of this square is A squared, and if I construct a square where the side is B, then it would look like this. Okay, so this area is B squared. And then I consider this side and a square with sides that is C. Like that. Okay, and then this area is C squared. So Pythagorean said that there's a relationship between these areas. He said that this c squared is always equal to a squared plus b squared. So this is what we call Pythagorean theorem. It's a very important theorem that you guys need to really understand and really use to solve certain expressions that will come in physics. So for example, if you want to solve for C, you can simply take the square root of a squared plus b squared. And let's say you want to find the side B, then you can solve for b squared, c squared minus a squared, and then find b. Take simply the square root of c squared minus a squared. Okay, and if you want to find a, again, a squared, you can write it in terms of c squared minus b squared, and a is square root of c squared minus b squared. So that means if you know two sides, you can simply get the other side, okay, using Pythagorean theorem, and then that's very important. So, for example, let's say you have a right angle triangle like this, and let's say this is in our example, this is I told you that that's 4 units, and this is 3 units. You want to find the length of this longer side. How do you do that? We can use Pythagorean theorem. I identify 3 as A and 4 as B, and I need to find C. I simply use this Pythagorean theorem. So c squared is equal to a squared, which is 3 squared, and b squared, which is 4 squared. And then if you see, I can use this to find c, that is the square root of this entire thing, 3 squared plus 4 squared, which is square root of 25, and the answer is 5. Okay, so that's how you use Pythagorean theorem to find an unknown side of a given right angle triangle. If the other two sides are given, you can use this very quickly to find the third side, the dimension, the length of that third side. So this is Pythagorean theorem. Here we are going to study radians and degrees, two important ways of quantifying angles. Also, these are important when we discuss trigonometric functions, and also you should know how to convert between radians and degrees. So let's start by defining what is a radian. Here you can see I have a circle, and I'll define the center of that circle, and let's assume that the radius is r. What I'm going to do is that I'm going to take an arc length that is equal to the length of the radius of this circle. So let's say that's the arc length, the length of the arc length. So this is arc length. And its length is equal to the radius. And in that case, you can see this arc length will subtend an angle at the center of the circle. This angle is what we define as a radian. So the size of that angle is called 1 radian. In terms of degrees, 1 radian is equal to 57.3 degrees. Okay, so a radian is the angle subtended at the center of the circle when arc length is the same as the radius of the circle. Okay, so keep that in mind. That's very, very important. Now, how do we generalize this to a different angle, to an arbitrary angle? So again, let me draw a circle like that. And then this is the center of that circle. And now I have an angle like this. So this is the arc length. And let me call that arc length as S. Now what I'm going to do is that this is the radius. I'm going to break this arc length into in terms of the radius, of the circle. So there could be one radius over here, and there's another radius here, and then part of the this could be another fraction of a radius. So what I need to do is that I need to get that arc length and then divide that arc length by the radius, and then this ratio is equal to the angle subtended at the center in radians. This is a very important equation, so we can rewrite this equation as S equals R theta, where theta is measured in radians. So keep this in mind. This is going to be very, very important in the coming chapters when we discuss physics. Okay, so that's how you define the radius. 1 radian is equal to 57.3 degrees, and then this is a general expression to find the angle in terms of radius. You are given the arc length, you already know the radius, and then using this equation you can find the angle subtended at the center in terms of radians. Now another important, so this is the first one that is important, definition of the radius, radian, and then this is this very important relationship, and the third one I'll show it over here. What is the angle subtended by the circumference of a circle? So that's another important thing. So you have a circle like this, okay, and then this is the center, the circumference. So it's now the arc length is a special value. It's the entire perimeter of the circle. C is equal to 2 pi r, that is the circumference, but in this case the arc length is equal to C, or 2 pi r, the circumference. So what is the angle in terms of radians for that particular situation? We can simply use this relationship. For S, I'm going to substitute 2 pi r and then divide by r cancels out. So theta in this case is 2 pi radians. So the circumference subtends an angle 2 pi radians at the center. We already know that angle in terms of degrees, which is 360 degrees. So now we have another relationship between radians and degrees that can be used to convert between these two units. That is 2 pi radians is equal to 360 degrees. So this is another important relationship that you should know. These are important also when we study trigonometric functions, or sometimes they are called trigonometric ratios. So let's do some examples related to radians and degrees. Here what we need is to convert these degree values to their radian values. So I'll use the previously established relationship between radians and degrees. If you recall, I said 2 pi radians is equal to 360 degrees. So in other words, 1 radian is equal to 360 degrees divided by 2 pi, or we can simplify this and say that's 180 degrees over pi. So 1 radian is 180 degrees over pi. And another important relationship is 1 degree is equal to pi over 180 radians. Okay, so I basically inverted this where I solve for 1 degree. Here you can see it's solved for 1 radian, but this is for 1 degree. So I'm going to use this in order to convert these degree values into their radian values. So 10 degrees, I can write this as 10 times 1 degree. Okay, and for 1 degree, I'm going to make the substitution. 10 times pi over 180 radians. And then you can see the answer is pi over 18 radians. Similarly, I can do 30 degrees. 30 times 1 degree equals 30 multiplied, instead of 1 degree, I'm going to substitute pi over 180 radians. And then the answer over here is pi over 6 radians. And then 60 degrees, again 60 times 1 degree, 60 multiplied by pi over 180 radians, and you can see this is pi, when you simplify this, pi over 3 radians. And then final one, 120 degrees, again I can break this into 120 multiplied by 1 degree, and I'll substitute for 1 degree pi over 180 radians, like that. And then further simplification will give me the answer 2 pi over 3 radians. So this is how you convert from degrees to radians, and this is very important. In the coming chapters, you will see we are going to use this very frequently, and this whole idea of converting from one unit to another unit is called unit conversion, and in a separate video I will again discuss some of these examples. Okay, so now let's go to the next one. Here we are doing the reverse, that is, we are given the radian values and we need to find the degree values. So in this case, I'm going to use that 1 radian is equal to 180 degrees over pi. So this is the conversion factor. We usually call this the conversion factor to make the conversion from radians to degrees. So the first one, 5 pi over 6 radians, I can rewrite this as 5 pi over 6 times 1 radian, and then for 1 radian I can substitute 180 over pi. 5 pi over 6 times 180 degrees over pi, and when you simplify this, you will get the angle as 150 degrees. So that's 150 degrees. And then the other one, 7 pi over 8, 7 pi over 8 radians. Again, I can break this into 7 pi over 8 times 1 radian, and I'll substitute for that 1 radian 180 degrees over pi. And then simplify this, and you should get the answer as 157.5 degrees. Yes, that's the answer for the second example. The third one is 3 pi over 2 radians, and again 3 pi over 2 multiplied by 1 radian. So now I guess you get the idea on how to do these calculations. 180 over pi. So then here you are going to get 270 degrees as your answer. Okay, and then the last one, 9 pi over 10 radians. So that means again 9 pi over 10 multiplied by 1 radian. I'm substituting for that 1 radian, 180 degrees over pi. And then when you simplify this, you can use a calculator and find the answer. But I get 162 degrees for the answer. So that's how you convert from radians to degrees. So this is what we used. It's usually called the conversion factor, and we used a similar conversion factor over here when we converted from degrees to radians. So that's basically it for radians and degrees. In this section, we are going to talk about trigonometric functions. So we always measure an angle relative to the positive x-axis. So this is our positive x-axis. Okay, and that's considered 0 degrees, and we always go counterclockwise direction, and that's considered the positive orientation. So if it's 0 here, then this is considered 90 degrees, and this is considered 180 degrees. This is 270 degrees, and when you come back to the same original position, you have completed 360 degrees. Okay, now you can express the same thing in terms of radians. 0 radians. Over here it's pi over 2 radians. Over here it's pi radians. Over here it's 3 pi over 2 radians, and then coming back to the original position, you have completed one whole circle, so that is 2 pi. So if you have any angle in the first quadrant, you should know that it should be between 0 degrees and 90 degrees. In the second quadrant, if it's in the second quadrant, then the angle should be between 90 degrees and 180. In the third quadrant, 180 degrees and 270 degrees. So like that, okay? So again, an important convention, counterclockwise angles are considered positive. Clockwise angles, they are considered negative angles. So for example, let's say that in the first quadrant I am measuring an angle, and let me call this 30 degrees from the positive x-axis, and you can see it's a positive number. Now if I measure the same angle, let's say relative to the positive x-axis in the clockwise direction, that's going to be negative 30 degrees. Okay, it's not positive 30 degrees, it's negative 30 degrees. So that's the important thing that I want to discuss. Depending on the quadrants, you should know how to identify the range of the angle, and depending on the orientation you measure angles, whether it could be counterclockwise orientation or clockwise orientation, the angle could be positive or negative. So keep that in mind, that's going to be very important. Now let's look at just the first quadrant. And what I'm going to do is that I'm going to draw a right angle triangle, ABC right angle triangle, in the first quadrant, like this. And then you can see why this is a right angle triangle, because you have a 90-degree angle. And I'm going to name it, let's say A, B, and C. Okay, and then let me define this angle. You can see positive x-axis. This is the first quadrant. So this angle, this is theta degrees. And you can see from the geometry, this theta has to be less than 90 degrees and it should be greater than 0 degrees because it's in the first quadrant. Now, relative to this angle theta, I can define BC, the side BC, as the opposite side. So that's going to be the opposite side. And then relative to theta, AC is called the adjacent side. And then AB is called the hypotenuse. Now, using these three sides, we can define trigonometric functions. So the first trigonometric function that I'm going to define is called sine theta. So it's defined as the opposite side divided by the hypotenuse. So opposite is BC, and you can see hypotenuse is AB. Let me call this equation number 1. The next one is cosine theta. So cosine theta is defined as the adjacent over hypotenuse. Adjacent is AC over hypotenuse is AB. And the third one that I'm going to define is called the tangent theta. And that's defined as the opposite over the adjacent. The opposite is BC and the adjacent is AC. So that's, let me call that equation number 3. Now what I'm going to do is I'm going to divide equation 1 by equation 2 like this. So that means I have equation 1 sine theta. So equation 1 over 2 means sine theta over cosine theta. But sine theta is this ratio BC over AB. And then cosine theta is the ratio AC over AB. You can see these AB's in the denominator of the first term and in the denominator in the second term, they cancels out, and then you get BC over AC. So from equation number 3, you can see BC over AC is nothing but tangent theta. So then we get something called a trigonometric identity. So that means tangent theta can be written as sine theta over cosine theta. So this is a very important trigonometric identity. You should keep this in mind. Now let's square equation number 1 and equation number 2. So if we square equation number 1, I'm going to get sine squared theta, that is equal to BC squared over AB squared. And then when I square equation number 2, I'll get cosine squared theta is equal to AC squared plus AB squared. Now I'm going to add these two together. So 1 squared plus 2 squared. And that's going to give me, on the left hand side, I'll get sine theta, sine squared theta plus cosine squared theta equals BC squared over AB squared plus AC squared over AB squared. You can see there's a common denominator, AB squared, and in the numerator I can rearrange this as AC squared plus BC squared. Now, what is AC squared plus BC squared? If you look at this right angle triangle, AC is the adjacent side, BC is the opposite side. So the numerator over here is basically the square of the adjacent side plus the square of the opposite side. So simply that gives you a way to apply Pythagorean theorem to this right angle triangle. So if you apply Pythagorean theorem, then you will get to this right angle triangle ABC, you will get the square of the hypotenuse is equal to the sum of the squares of the other two sides. That is AC squared plus BC squared. So that comes from the Pythagorean theorem, which we discussed earlier. So I'm going to apply Pythagorean theorem, and then you'll see this would be AB squared. Okay, and then we are simply going to get AB squared in the numerator, AB squared in the denominator, and simply it's equal to 1. So this is another very important trigonometric identity where you get sine squared theta plus cosine squared theta is equal to 1. Okay, let's look at some trigonometric identities that will be useful in our course. Now, these identities, when you are using them in solving problems, you don't need to derive them or prove them. You can just simply use them. So let's consider if theta is measured in, where theta is an angle, it's measured in either radians or degrees. Then the following identities are useful for physics problem solving. So the first set of identities, sine 2 theta equals 2 sine theta cosine theta. Okay, so as an example, let's say you have sine 60 degrees. You can expand this as 2 sine 30 degrees multiplied by cosine 30 degrees. Sometimes it's called the half angle identity because you have 2 theta here and thetas here. And now the corresponding cosine to theta can be written as cosine squared theta minus sine squared theta. Again, as an example, you can think about, let's say, cosine 120 degrees. So that's the same as saying cosine squared 60 degrees minus sine squared 60 degrees. Okay, so this is the first set of identities. The second set of identities that will be important are like sine 90 minus theta. So if you have sine 90 minus theta equals cosine theta, and then cosine 90 minus theta, that's equal to sine theta. So in the xy coordinate system, these two equations or identities are related to the first quadrant. First quadrant. The third set of identities that I want to discuss are these. Sine 180 degrees minus theta equals sine theta. Then cosine 180 degrees minus theta equals minus cosine theta. So keep in mind the sign change, okay? Cosine minus cosine theta. And then the tangent 180 degrees minus theta equals minus tangent theta. So these are relevant for the second quadrant. If you think about again the xy coordinate system, these are relevant in the second quadrant. Especially this one will be very important when we talk about graphing. So that will be the next section that I'm going to talk about after trigonometric functions, graphing. And in graphing, we usually need to find something called the slope of a curve, rise over run. And when we do that, you'll see this trigonometric identity will be very important. The final set that I want to talk is identities in the fourth quadrant. So sine minus theta equals minus sine theta. So minus theta here is the angle measured in the clockwise direction. As I told you earlier, when you measure an angle, it could be degrees or theta, it doesn't matter. If you measure the angle counterclockwise, it is positive, but clockwise, that's negative. So this angle is measured clockwise and it goes to the fourth quadrant. The next one, cosine minus theta, so that's going to be cosine theta. And then finally, tangent minus theta is equal to minus tangent theta. So these are relevant for the fourth quadrant in the xy plane. Remember, for this theta, you can have radians or degrees, it doesn't matter. So, I mean, as an example, if you think about sine 90 minus theta, you can have something, let's say, sine, this is an example, 90 minus 30 degrees. Okay? And according to this, that is equal to cosine 30 degrees, right? Because this theta is this 30 over here. And then you'll have sine 60, because 90 minus 30 on the left hand side, that is 60. So sine 60 is equal to cosine 30 degrees. So you can use a calculator and verify this if you want to do that. As an example, for this set of identities, I can have sine, let's say 180 minus 20 degrees, where theta is this 20, and that is equal to sine 20 degrees. So 180 minus 20 is sine 160 degrees equals sine 20 degrees. Okay, so that's an example for this third set of equations, identities. And for the final set of identities, I can have this as the example. Let's say cosine minus 45 degrees is equal to cosine 45 degrees. Or you can have tangent minus 60 degrees is equal to minus tangent 60 degrees. So again, remember, you can verify this using the calculator, and these are all valid for theta when theta is measured in radians, as well as when it's measured in degrees. Now let's look into graphing some of the trigonometric functions, especially sine theta and cosine theta. So here you can see a table where I have listed angles in degrees and their corresponding angle in radians, and the numerical value for the sine theta, that is the sine theta value. And pretty much what we have is a function like this: y equals sine theta. So sine theta goes to the y-axis, which is going to be our dependent variable, and then theta is the independent variable. And let's consider it's measured in degrees over here. So if we plot these values, you will see that you're going to get a curve like this, and you put the data points, and then you can connect the data points, and then you will see something like this. So this is what we call a sinusoidal function. It's called a sinusoidal function because it looks, it pretty much looks like a sine function. So that's why it's called a sinusoidal function. So this is an example for a sinusoidal function. So here you have 0, and then at this highest point it corresponds to 1, and then the angle over there is 90 degrees. And here the 0 value, that corresponds to 180 degrees. And then this maximum value, however, that's in the negative direction, that maximum value corresponds to -1, and the angle over at that moment is 270 degrees. And then over here you have 360 degrees. So this is what we call a sine wave, a sine function. Very important. It's a very important model when we discuss oscillatory motion, oscillatory motion, simple harmonic motion. Then you will see this function will be very important. So if we look at the maximum value and the minimum value for a sine function, that's given as the maximum value sine function can obtain. You can see that's +1. The minimum value the sine function can obtain is -1. Now this height over here from this x-axis to the maximum displacement, we have a special name for that. You will learn this later on. It's called the amplitude. And similarly on this side we have the same amplitude. Maximum displacement from the equilibrium position or the equilibrium line. So this separation, that's amplitude. Okay, so I hope this gives you some basic idea about the sine function. Now let's look at the cosine function. It's going to be the same kind of process. I have again listed a table. You can see the theta values in degrees, their corresponding values in radians. And then what we can do is we substitute for this angle using a calculator, and then we can get the numerical value for cosine theta. So again, y equals cosine theta. So that's the function where theta is the independent variable and y, or cosine theta, is the dependent variable. And again, I'll use the angle in terms of degrees. And then here, when you plot this curve, you can see at zero angle, cosine theta is 1. So that's somewhere here. That's +1. And then you can see at 90 degrees, cosine value is 0. And then at 180 degrees, it's -1. And 270, it's 0. 360, it's 1. So you can see the profile is different from y sine theta function. So it's going to look like this. It's going to decrease. And then at 90 degrees, it'll be 0. And then at 180 degrees, it will reach a maximum value in the opposite direction. So that is like -1. And then, so here 90 degrees. Over here, it will be 180 degrees. And then it's gonna go like this. And when it crosses the x-axis again, that would correspond to an angle of 270 degrees. And then it will reach to its maximum value over here. And that corresponds to 360 degrees. So you can see, I mean, this is just a sketch. It's not perfect, but I believe you get the idea. Again, what you can see is that the cosine function also has a maximum value and a minimum value. Cosine theta, the maximum possible value is 1. The minimum value it can take is -1. Cosine theta, sine theta, these periodically varying functions are called sinusoidal functions. So again, just to remind you, this separation is what we call the amplitude. That is the maximum displacement from the equilibrium position, or in this case, from the horizontal x-axis. Okay, so these are the only two functions that I'm going to graph for trigonometric functions, that is y equals sine theta and y equals cosine theta. You should have some idea about at least identifying these functions. When you see a function like this, you should very quickly identify that this has to be a trigonometric function. It's a sinusoidal function like that. So that's very important. Okay, let's wrap up this section by doing two examples. The first example, according to the given right angle triangle, so ABC triangle is right angle triangle, sine theta is 3/5, determine cosine theta and tangent theta. So you are given sine theta as 3/5. So then the first thing that you have to remember, the definition of sine theta, right? So sine theta is what? It's basically the opposite side of the right angle triangle divided by the hypotenuse. Okay, so now let's go to the right angle triangle, and relative to the angle, let's try to identify what is opposite, what is the hypotenuse, what is the adjacent. Opposite to the angle, that is by definition the opposite side. The longest side is what we call the hypotenuse. And then adjacent to the angle other than the hypotenuse is the adjacent. So that means we are given sine theta is equal to 3 over 5. So that means opposite has to be 3 units and hypotenuse, it has to be 5 units. So this is 3 and this is 5. We have a right angle triangle. Two sides are given, are known. We need to find the third side in order to find the cosine value and the tangent value of this angle. So how do we find this AC length? We can use Pythagorean theorem. According to Pythagorean theorem, we have AB squared equals AC squared plus BC squared. Okay, so then what we need to do is we need to solve for AC. So I can rearrange this. AC squared equals AB squared minus BC squared. And AC is the square root of AB squared minus BC squared. So I'll make the substitution now. AB is 5, so I have 5 squared. BC is 3, so I have 3 squared. And that's the square root of that entire thing is equal to AC. So AC is 25 minus 9, so that is 16. So I'll have square root of 16, which is 4 units. So AC is going to be 4 units. So now we know the hypotenuse, we know the opposite side, and we know the adjacent side in terms of their lengths. Now we can find the cosine theta as asked in the question. So cosine theta is the adjacent divided by the hypotenuse, which is 4 over 5. Okay, so this is given in our question, but this is one that we actually figured out. And then the other one, tangent theta, by definition that's opposite side divided by the adjacent side. And opposite is 3, adjacent is 4. So tangent theta is 3 over 4. So that's how you figure out the trigonometric functions in this particular example. Now, a very important thing to note here, I will talk about this when I discuss vectors, but still there's something important that you should know. So let me use a different color to explain this. So if we have a right angle triangle, let's say that's our right angle triangle. And then this is the angle theta. And let's say this length is given as L. This is L. And we want to figure out this side, let's call it Y. And this side, it's X. How are we going to do that? We can simply use the definitions of sine theta and cosine theta to do this. We need to identify that L stands for the hypotenuse, this Y stands for the opposite side, and this X stands for the adjacent side relative to this angle. That's the first thing that you need to identify. And then apply sine theta, the definition of sine theta, opposite over hypotenuse, Y over L. And then you can see the other one, cosine theta. By definition, that's the adjacent over hypotenuse. Adjacent, as we identified, that's X over L. So now you can find Y, X and Y in terms of L and theta. Simply solve for Y. You can see Y equals L sine theta, and then x is equal to L cosine theta. So you'll see later on in the vector review as well as during the course, you'll see this sine component and the cosine component. How to find the sine component, cosine component would be extremely important. So keep this in mind because this is very, very important. Okay, so this part is important. Now let's go to the second example. So this is the second example. Again, it uses geometry and some basic trigonometry that we discussed. Find the length AC, the length of side AC of the given triangle ABC. So you can see ABC triangle. We need to find this distance. So let me call that L. We need to find a value for L. If you look carefully at this triangle, you can see sides AB and BC are equal. When two sides of a triangle are equal, we say that's an isosceles triangle. So that's an isosceles triangle. And another important thing in such a triangle is these adjacent angles are equal to one another. So I'll represent those two angles by theta. So this is theta. This is also theta because it's an isosceles triangle. This length equals this length. And then we also know a very fundamental geometric rule, principle, saying that the sum of the two opposite angles, so sum of the two opposite angles, that means these two angles, is equal to the exterior angle. So that's the exterior angle. So that means sum of these two angles, which means 2 theta, is equal to the exterior angle 60 degrees, and from there we can find theta is equal to 30 degrees. So this angle is 30 degrees and this angle, that's also 30 degrees. Now the objective is to find this length AC. What I'm going to do now is to draw a perpendicular line from point B to AC. So this is a perpendicular drawn to AC, and this line actually bisects this angle. So that means this angle equals this angle. So we have this angle over here equals this angle. The sides BC is 10, and that's the same as the side AB, which is also 10. We have the perpendicular line common to both of these triangles. As a result, this length AC is divided in half by this perpendicular line, and we have two congruent triangles. So let me call this point D over here, and then we have ABD and CBD triangles which are congruent to one another. Triangle ABD and triangle CBD are congruent. So that means they have their angles are the same, their sides are the same. As a result, I can write this length AC in terms of AD. So you can see AC can be broken down into AD plus DC, But since these two smaller triangles are congruent, I have AD equals DC. So that means I can rewrite the right hand side as AD plus AD equals 2AD. So instead of finding AC, what I can do is that I can find AD and multiply that value by 2. So how do I find AD? What is AD? AD is this side of this smaller ABD triangle. And the important thing is that that's a right angle triangle. So let me highlight that right angle triangle so it's more clear. So this is that right angle triangle. You can see this is the 90-degree angle. This 10 or AB is what we call the hypotenuse. And then this side, which is opposite to the angle theta, is what we call the opposite by definition. And then this has to be the adjacent side. So now I can go ahead and define the trigonometric functions that we discussed earlier. Actually, I'm going to define cosine of the angle, cosine theta. So if you look, cosine theta is equal to adjacent divided by the hypotenuse. Adjacent is AD and hypotenuse is AB. Now I can substitute the values. Theta is 30 degrees, so cosine 30 degrees is equal to AD. That is what I need to solve for this problem, and AB is 10 units. So you can see AD is simply 10 times cosine 30 degrees. Now from this equation, let me call that equation number 1. From 1, I get AC is equal to 2 times AD, which is 2 times 10 cosine 30 degrees. And now you can use a calculator to find the answer. You'll see that the answer is 17.32 units. So that's how you do this example. Here we use some basic rules in geometry as well as the definition of one trigonometric function, namely the definition of the cosine function. In this section, we are going to talk about graphing. I will discuss two types of graphs, linear graphs and nonlinear graphs. Now, graphs are plotted on an XY coordinate system. So here we have two perpendicular axes. The horizontal axis is usually called the x-axis, that's the positive x direction to the right. And then the vertical axis, that's called the y-axis. In this direction, the upward direction, that's called the positive y direction. The two axes intersect at this point, and that's our origin, the point 0 or 0, 0 coordinate. Now, what is a linear equation or a linear relationship? Let's say that we have y and x variables. Now, if you recall, x variable is also known as the independent variable. And the y variable is called as the dependent variable. So if we have a relationship between this independent variable and the dependent variable, like in this form, you can see x and y are directly proportional to one another. I discussed this symbol in a previous section. They are directly proportional, x and y, and you can see their exponents are 1. So this sort of a relationship is called a linear relationship. Now I can multiply this by a proportionality constant, let me call that m, and then the relationship becomes an equation, y equals mx. So we have this type of a linear equation or a linear relationship, or we can have it in this way: y proportional to minus x. Instead of plus x, now we have minus x. So again, I can multiply the relationship by a proportionality constant, and then I will have this equation. I'll call that proportionality constant m prime. Okay. Now I will discuss y equals minus mx later. However, let's focus on y equals mx. The y equals mx equation, its graph on this xy coordinate system would look like this. It's a straight line that goes through the origin in this way. And that's what we call y equals mx line or the graph. Now, another important thing is defining the slope or the gradient of a line. That is very important. Again, we'll consider our xy coordinate system. And then I'll draw our y equals mx line that goes through the origin like this, y equals mx. The slope or the gradient is defined in this way. The slope is defined as the rate of change of y variable with respect to x variable. That is how we define the slope of a straight line. So in terms of the x comma y variables, slope can be defined as delta y over delta x. So what is delta x and what is delta y? If we look at this line y equals mx, let's first define 2 points on the line. Let me call one point as a, x1 comma y1, and the other point, let me call it b, x2 comma y2. So in terms of those coordinates, delta y can be written as y2 minus y1, and delta x is x2 minus x1. So in other words, delta y is the vertical separation between the 2 points A and B. Delta x is the horizontal difference between the 2 points A and B. In other words, we call these rise and run. This is delta y is the rise and delta x is the run. So we can further write this as rise over run. So that is another common way of defining the slope of a line. Just find the rise over run and you get the slope. Another one I need to point out, if you can identify this triangle, let me call this point C. So then ABC triangle is a right angle triangle. And let me define this angle in a different color. So let me call this angle theta. Okay. And then you should be able to identify what delta y and delta x are. So delta y with respect to this angle for this right angle triangle, delta y is the opposite side and delta x is the adjacent side. So in other words, I can write down from our trigonometric identities delta y over delta x is equal to tangent of that angle theta. So we have three methods to define the slope. This is the first way of defining the slope. This is the second way of defining the slope, rise over run. And then this is the third way of defining the slope. Simply look at the angle the line makes with the positive x-axis and then take the tangent of that angle. So these are the three more common ways of defining the slope or the gradient of a line. If you look at this equation y equals mx, you can notice that if we solve for m, we get m equals y over x. Or if we look for a change in the variables, then we can write it as delta y over delta x. So in that sense, this m is what we call the slope. So slope is basically m in a linear equation like y equals mx. M stands for the slope. The first definition, it says it's the rate of change of y with respect to x variable. Another way of defining is delta y over delta x, where delta y stands for the rise and delta x stands for the run. And the third way of defining m or the slope is simply consider the angle the line makes with the positive x direction and take the tangent of that angle. Let's consider three linear equations. I will take y equals x, then y equals 2x and y equals 4x. So if I plot these three lines on this xy coordinate system, I'll have y equals x like that, and then y equals 2x like that, and then y equals 4x like that. So you can see when this number over here, when that is increasing, over here it's just 1. That's why I haven't written that down. But when that number increases, the steepness of the line increases. So slope qualitatively is related to the steepness of the line. and that is also very important. So for example, over here 4 is the slope, because I told you this is in the form of y equals mx, and we call m the slope. So this is 4. So it has the highest steepness, the most steeper line. Then y equals 2x, it has a steepness like this, and y equals x has a steepness like this. So that means the angle increases. Steepness increases means the angle the line makes with the positive x-axis, that increases. So that's another way of identifying the slope. Simply look at the steepness of the line. Okay, let's do this example. Find the gradient or the slope of the line given, and also find the angle it makes with the positive x-axis. So as we know, m gives you the slope, and that is defined as the change in y divided by change in x, or I can further write it like y2 minus y1 divided by x2 minus x1. So I'll consider this coordinate as my x2, y2. So x2, and this would be y2, and this is my x1, and this is my y1. So I'm going to substitute, and then you'll see it's like 4 minus 2 divided by 6 minus 1. So I get 2 over 5, or in other words, that means 0.4. So the gradient or the slope of this line is positive 0.4. So that's part 1. The next one, find the angle it makes with the positive x-axis. So that means, if you construct a right angle triangle, it's this angle. Let me call that theta. So we all also know that m, or the slope, is defined as tangent, trigonometric function, tangent of this angle, tangent theta. So if I want to find theta, I can take the inverse tangent and I'll get theta. So that means if I take the inverse of this, I can solve for theta. So that means inverse tangent of m. Okay, and then I have inverse tangent. What is m? We figure that out, 0.4. And then you'll see theta is equal to approximately 21.8 degrees from the positive x-axis. So you can see this angle is less than 90 degrees. So that's how you solve this problem. Now, another important thing, this m is 0.4. That means for any point, any point along this line, the slope is constant. So that means I'll use a different color. For example, let's consider a point over here, and then you draw a tangent to that point like this, and that makes the same angle theta with the horizontal compared to this point. You draw a tangent and you look at the angle theta. It's the same theta. You draw a tangent here and you can see it's the same theta. If it's a linear or a straight line, then m, or the slope, is constant throughout that line. Let's look at some variations of the equation y equals mx, where m, or what we call the slope, is a positive value. So the first one, I'm going to draw y equals mx. We already know the form of this graph. It's a straight line that passes through the origin like that, and then it's going to make an angle with the positive x-axis. Let's call that angle theta. So m is equal to tangent theta. So the next one I'm going to draw a variation of y equals mx is y equals mx plus c, where c stands for the y-intercept. So that equation, that line, is something like that. It makes the same theta with the horizontal because you have the same m. So the steepness or the slope is the same. But now it does not go through the origin, but it goes through a point on the y-axis, which we call the y-intercept. So the coordinates of this point is 0, c, where c is the y-intercept. The other variation is y equals mx minus c, where c again is the y-intercept, but in this case, the line is like this. So it makes the same slope, that means the same angle with the horizontal, but this time it's going to intersect not above the x-axis but below the x-axis. So the coordinate of that point would be 0, minus c, where the y-intercept is minus c. So these are some variations of y equals mx equation when m is positive. Now let's look at y equals mx when m is a negative value. How will these lines look like on a xy coordinate system? So for example, let's consider y equals minus 2x, this linear equation. So if we plot this linear equation on this xy coordinate system, it's going to look like this. So that's your y equals minus 2x line. The important thing here is the angle the line makes with the positive x-axis. So this is theta. Here, theta is going to be larger than 90 degrees, but it will be less than 180 degrees. So that means the angle is always in the second quadrant. In this case, if we take tangent theta when theta is in the second quadrant, you'll see that the tangent theta value is always less than 0, or it's a negative value. So that's why you have this negative sign. If there's a negative sign in front of the coefficient, then the slope looks like this. Now the variation, another variation of this is with the y-intercept. So let's say that y equals minus 2x plus 1. So this line will intersect the y-axis at 0, 1. So it's going to look like this. And then this y-intercept would be 0, 1. So the general form for this is like y equals mx plus c. But remember, m is less than 0. This is y equals mx, but m is less than 0. In the previous case, we talked about when m is positive. The third variation is y equals minus 2x minus 1. So that means the line would go like this. And then this coordinate would be the y-intercept. This time it's going to be below the x-axis. 0, minus 1. And the general form would be y equals mx minus c with m less than 0. So these are the main types of linear graphs that I want to discuss that will be relevant for our course. Now let's look at some nonlinear graphs that are going to be important for our course. So the first one, again, I'll define these called the axes. This is y, and this is going to be x-axis, and that's our origin. Now, what is a nonlinear graph or a nonlinear relation or a nonlinear equation? So you would still have your independent and dependent variables like this, and then they are related to one another, but this time the exponents are not 1. For example, the exponent here could be 1, but the exponent on x could be like 2. This is an example for a nonlinear relationship. So then I can use this proportionality constant. Again, let's call that proportionality constant m, and then I'll have y equals mx squared. So how would we plot this graph? So it's going to look like this. It will be definitely a curve, not a straight line. It's going to look like this. So y equals mx squared. Now, what is the slope of this curve? So the slope for this curve is position dependent. So for example, if I consider 2 points A and B, how do we find the slope? We draw a tangent to that to the line at that point. So let me use a different color for that. So if I draw the tangent for A, it's going to look like this, and then I can figure out the angle it makes. Let me call it theta, and here again I'm going to draw a tangent to point B, and then I'll define the angle with the positive x-axis. Let me call that theta prime. Obviously you can see theta and theta prime are different, so the slope changes along this line. It's not constant like in the linear case. Here actually we can show that the slope is equal to 2x instead of just a constant. So it's not a constant value. So that is something very important with the nonlinear graphs or equations. The slope depends on the position. In a linear equation, the slope is constant. Okay, but we are not going into these details, but keep that in mind. If you're asked to draw a sketch y equals mx squared curve, then it's gonna look like this. The next one, again I'll define my y and x coordinates. Again, a nonlinear relationship. Let's say this time it's going to be y equals mx, but x is 1/2. The exponent is 1/2. So if you plot this one, it's going to look like this. So that's your y equals mx 1/2 graph. Again, you'll see the slope is different from point to point. You can select 2 points, then draw the tangent at those 2 points, measure the angle between that tangent line and the positive x-axis. You will see the angles are different. So the steepness, the slope changes from point to point. The next example is y equals 1/x. So if we plot this curve, the nonlinear equation, it's going to look like this. So that's your y equals 1/x graph. Similar to that, there's another very important nonlinear equation. That's y equals 1/x squared. So this is called the inverse square law. because you can see 1 over means inverse. If you see x squared, that's what it meant by square. So this variation is called the inverse square law, and you'll come across different models that explains this inverse square law. So if we plot 1 over x squared on this same plot, it's going to look like this. It's much more steeper than 1 over x. So it's like this. So this is 1 over y equals 1 over x squared, and this intersection point is coordinate 1, comma 1. So you can see compared to 1 over x squared becomes 0 very quickly. So this 1 over x will take some time to become 0, but 1 over x squared is much more steeper and it will reach 0 very quickly, or it's decreasing much more quicker than 1 over x function. The next nonlinear equation that I'd like to discuss is y equals minus 1 over x. This graph is between the positive x-axis and the negative y-axis, and it's going to look like this. So you'll see that as it reaches, as the x value increases, it will have a horizontal asymptote, and as the y value increases in the negative direction, it will have a vertical asymptote. So this is another important nonlinear graph for our course. The fifth example that I'd like to discuss is the exponential function y equals e to the power minus x, which we defined for x equal or greater than 0 region. Then the function or the nonlinear graph would look like this. And this intersection point, the y intercept it will be 0, 1. The sixth and the final nonlinear equation that I'd like to discuss is y equals 1 minus e to the power minus x. So if we plot this curve, it's going to look like this. As x increases, the y value will reach 1. So that means we have a horizontal asymptote at y equals 1. So this line is the y equals 1 line. Okay, so this is the final nonlinear graph that I'd like to discuss, that I feel like will be important for our course. So with this, I conclude the math primer for college physics. And in the next video, I will talk about SI units, unit conversions, and significant figures.